is Mr. Aiden. This is the AP Physics C Mechanics Free Response question number 2. This is from the 2025 exam. I think it was on May 3rd, 2025. And this is the brand new format of the AP exam. So question number 2 is always going to be what's called the translation between representations problem, the TBR problem. This is a 12-point, this is the long baby, and this is the suggested time of 25 to 30 minutes. And so they're going to ask you to do a few different things on these TBR problems. We're going to connect different representations of a scenario by doing the following: creating visual representations, deriving more mathematical equations, drawing graphs of those related quantities, and or one of three things: justifying consistency between two representations, predicting and justifying another situation, or predicting and justifying if scenarios were altered. Those are the TBR problems. So let's get to problem number 2. This was a spring problem, a little bit of an oscillations problem, a little bit of an energy problem. You can see it says in scenario 1, a system is composed of two springs. We got spring A, spring B. We have a block of mass M is at rest at its equilibrium right there at x is equal to 0. You can see each spring is attached. Spring A has a spring constant of K. Spring B has a spring constant of 2K. That's something to keep in mind. It's at its relaxed length. And then they move it to x1. So then they move this x1. It's held at rest, which means it has potential energy from spring A. It has potential energy from spring B. We're going to give the positive x direction is to the right. And you can see it says an energy bar graph. You can't drink yet if you're going to be doing this AP exam, but you're going to be doing some bar graphs here. It can be used to represent the elastic potential energy, the potential energy of spring A and the spring B, and the kinetic energy. And we're going to take a look at what's happening here. You can see we want to take a look at the potential of spring A is going to be 1/2 K, and we are x1 squared, where potential energy of B is going to be 1/2 of 2K, and that's brought to x1 squared. It's at rest, which means the kinetic energy is 0 here. And so we're going to do a little bar graph here. And so we're going to do a bar graph of the potential energy of A. You can see that's going to be, we're going to consider this to be 1/2 of kx squared. So 1/2 of k x1 squared. So look at B. Potential energy of B is going to be 1, not 1/2, 1 kx1 squared, which means this is going to be kx1 squared up here. That's going to be as far as this is, and that's going to be our bar energy graph. If you did it lower, as long as it's proportional, you're good. And of course, the kinetic energy, it's at rest, so we're going to put a distinct line at 0 right here. And so that was question A, the energy bar graph. Now let's take a look at question B. Question B says the object's released and begins to oscillate. Okay, derive an expression for the velocity as it passes through this specific point. And again, we have to derive, we got to use some fundamental physics principles, which means we're going to use the conservation of energy. We're going to use the conservation of energy here. And how are we going to do that? The potential energy of A initially, plus the potential energy of B initially, plus the kinetic energy initially, is going to be the potential energy of A at this final point that we're going to consider our final point by frame of reference, plus the potential of B final, and plus the kinetic final right here. So what's the potential of A is 1/2 kx1 squared. What's the potential of B is kx1 squared. What was the kinetic energy? Was 0 initially. Now we're taking a look at what's happening with A at this point at x is equal to 1/2 of x1. So we have 1/2 of k times 1/2 of x1 squared, making sure to put that in parentheses, plus 1/2 of 2k times 1/2 of x1 squared, plus 1/2 of mv squared. And we're trying to take a look for this velocity right here. So we got to add some things up. We add at the beginning, we get 3/2 kx1 squared. If we add these two guys up, we're going to get 3/8 kx1 squared plus the kinetic energy of 1/2 mv squared. We're going to subtract, which means we're going to get 9/8 kx1 squared is equal to 1/2 mv squared. We're going to multiply by 2. We're going to multiply by 2, which means we're going to have 9/4. We're going to divide by m. So we have kx1 squared over m equals v squared. And so when we square root, we're going to get a final velocity of the square root of all of this stuff. The 9 and the 4 come out and become 3/2 from the square root. The x1 squared comes out of the square root, so we have x1. What's left in the square root is these constants k over m. And that is my final velocity of the block at this point, 1/2 of x1. That was question B. That was your deriving. You can see now we have scenario 2. The block is oscillating with a period of t. With a period of t, you can see one full oscillation is a period of t. Hope you can see this is a cosine graph here. We have a kind of a cosine graph going on here. We're going to oscillate from this positive x1 to this negative x1 right here. And we as a function of time. And what are they going to ask us? They're going to ask us what happens if the scenario changes a little bit. And it says there is now friction between this scenario. And we don't want the potential energy. Again, this was the position with respect to time. We actually want the kinetic energy with respect to time. So what's the kinetic energy when it's full at x1? The kinetic energy is 0, isn't it? What's the kinetic energy when it's back on the other side at negative x1? Well, the kinetic energy is back at 0, isn't it? What's the kinetic energy when it's back at positive x1? It's 0, and you can see it keeps hitting 0 kinetic energy right here. Where's the greatest kinetic energy, the maximum kinetic energy? The max kinetic energy is right here, isn't it? It's where the velocity is the greatest. Actually, the speed is the greatest. The velocity is the most negative here, then the velocity is the most positive right here. Now this scenario is when there's no friction. So the highest kinetic energy is going to be right here. But since there's a little bit of friction, that kinetic energy goes lower and lower and lower and lower and lower, eventually till it becomes 0. And so my graph is going to come up, down, up, down, up. It's easier to do this on paper. And you can see it's kind of looking like this oscillation graph that continues to decrease according to the non-conservative force of friction. Then it says in scenario 3, the block is replaced with a larger block mass. And it says the coefficient of kinetic friction between the new block is the same. So the coefficient of kinetic friction hasn't changed. We still release it from rest. The kinetic energy is plotted as a function of time. Describe one feature that would differ. Well, if we have a larger mass, we know there's going to be a larger mass. We know the coefficient of 3 is equal to the coefficient of 2. And force of friction is equal to coefficient of friction times the normal force. Since the mass is increased in scenario 3 here, since the mass is increased in scenario 3, the force of friction is going to be greater. And that as compared to scenario 2. And because since the mass is greater, the normal force is greater. If the normal force is greater, the force of friction is going to be greater. And since the force of friction is going to be greater in scenario 3 compared to the force of friction in scenario 2, there's going to be more energy that is dissipated. There's going to be more energy dissipated by the non-conservative force of friction, which means that's going to decrease the maximum kinetic energy, isn't it? With every single oscillation. So what's going to happen is the graph is going to actually have a lower maximum kinetic energy, which means if we come back to this graph, it's going to come over here, it's going to come back down, but you can see this graph is going to be lowered every single time because the force of friction is greater. The non-conservative force is lowering that maximum kinetic energy, and that is what's happening when we change our scenario another time in Part D. That was question number 2, 2025 AP Physics C Mechanics exam. Catch my other videos, catch Mr. Aiden.com. See you guys. Bye.